Welcome to 6.5 Work and Fluid Forces. So in this video we'll be looking at how to use the formula work equals force times distance in order to solve some typical problems. Sometimes this formula can be used. For example, we know that force itself is equal to mass times acceleration. So sometimes you'll see work equal to mass times acceleration times distance. Okay, so one thing we should note before going any further are the units. So we have SI units. These are the international system units. So for force, we have newtons. Typical unit of distance is the meter. And then the typical unit for work, sometimes you'll see it as a Newton meter. But then the more popular name for this is the joule. In the joule you'll see abbreviated as J. Okay, and the other popular units system that we use is the American or the British system. So for distance would be typically a foot. Force would be pound. And then for the work, these would be in units of foot-pounds. Okay, so let's take a look at the definition. So we formalize the definition with an integral of the force function. So we have f of x dx, and we integrate it from a to b. Okay, and the way we define it is the work done by the variable force in moving an object along an x-axis from x equals a to x equals b. Okay, so one example. The units of the integral are joules if F is in newtons and X is in meters, and it's foot-pounds if F is in pounds and X is in feet. Okay, so we have a mini example in here. The work done by a force of F of X equals 1 over x squared newtons in moving an object along the x-axis from x equals 1 to x equals 10 is, okay, so let's set up the integral then. So our work would equal, integral would be from 1 to 10. Our force function, 1 over x squared dx, which is something we could easily integrate. So we would get negative 1 over x and then we could plug this in, plug in the 10, so we have negative 1 over 10 minus negative 1 over 1. So that gives us negative 1/10 plus 1. 1 minus 1/10, that would be 9/10. Okay, and then because this was newtons and meters, the unit for work would be joules. So 9/10 joules. Okay, let's take a look at example 2. Find the work required to compress a spring from its natural length of 1 foot to a length of 0.75 feet if the force constant is K equals 16 pounds per foot. Okay, one of the things we have to note here is Hooke's law for springs. Okay, we're talking about a spring. So there's a series of problems specifically designed for springs. And one of the things we have to note is this formula, F equals K times X. So basically it says that the force required to hold a stretched or compressed spring, X units, from its natural length is proportional to X. Okay, K is what we call a force constant. Okay, so the first thing we need to note is we have to figure out how much the spring was compressed. Right, so let's picture the spring. Okay, so let's say that is 1 meter. And we're going to compress it. Let's draw another one underneath. This will be the compressed version. So that's going to be approximately 0.75. So what happened? It got compressed. Right? If the natural length was 1 meter, it got compressed a 1/4 meter. So we're trying to figure out the work done to compress the spring a 1/4 meter from its natural length. Okay, now the way we set this up is with the integral. So the integral would be from 0 to 0.25. Okay, and then we're going to put in here f of x. Now, so we get f of x from this Hooke's law, f equals kx. They told us what k was, 16 pounds per foot. So our f function is 16x. Okay, so our work is going to be equal to integral of 16x dx from 0 to 0.25. 0 signifies from its natural length, natural, whatever it naturally is without any stress associated with it. In this case, it's 1 meter. That's going to act as our 0. And then it was compressed a 1/4 foot, so that's our b bound. Okay, so let's integrate this. We would add 1 to this, that would be x squared, divided by 2. So that 16 over 2 is 8. And then we would go and plug in the 0.25 and the 0. Okay, so this means we have 8 plus 0.25 squared. I'm going to write that as a fraction. Minus 8 0 squared. So that means we have 8 times 1/16. And the second part is 0 here. So that's 8/16, which is 1/2. So 1/2 foot-pound. Right, feet. Okay, so just okay. Let's go on to the next. Yeah, original problem was feet. I used meters, but I think you guys get the idea. These are feet. Feet. Okay, next one. Spring has a natural length of 1 meter. So these are meters. A force of 24 newtons holds the spring stretched to a total length of 1.8 meters. Okay, find the force constant K. How much work will it take to stretch the spring 2 meters beyond its natural length? How far will 45 Newton force stretch the spring? Okay, so let's figure out our K value, since they don't tell us what K is. So to figure out our K, we have our formula F equals KX. Okay, now the force was 24 newtons. We're looking for K, and it was stretched to a total length of 1.8. Now the X is the distance that it was stretched, past the natural length. So you figure out, you're going to say 1.8 minus 1. It was stretched 0.8 meters. That's how you think about that. Okay. So now to figure out K, we divide by 0.8. Divide by 0.8. That means K would equal, that would be 240 over 8, which will be 30. Newton meters. Newtons per meter. So K is 30. So that means our force equation would be F equals 30x. Okay, so let's get to the next part. How much work will it take to stretch the spring 2 meters beyond its natural length? Okay, so for that, we set up the work integral. 2 meters beyond its natural length means we would set up the integral from 0 to 2. And then we plug in our force function, our F. Okay, so we integrate that. That would be x squared over 2. So it's 30 over 2, that would be 15. We'll plug in 2, we'll plug in the 0, so we have 15 times 2 squared minus 15 times 0 squared. The second half is going to be 0. 2 squared is 4. So we have 15 times 4. And this will be 60. So 60 joules. Okay, so those are some of our typical spring style questions. And there was a third part, correct? Let's see. How far will a 45 Newton force stretch the spring? 45 Newton force. So the force is 45 newtons. Okay, so that's pretty straightforward. We're going to plug that into our force equation, right? Our force function. We know that our force function, we just say F equals 30x. And the F that was given was 45. And then to solve for x, we divide by 30. Remember, x will give us the distance that was stretched or compressed. Okay, the 30's cancel. 45 divided by 30, that would be 1.5. So x would equal 1.5 meters. Okay, so 45 Newton force will stretch the spring 1.5 meters beyond its natural length. Okay, so think about what that means. If your spring is already 1 meter, right? This is going to stretch it 1.5 meters beyond its natural length. So your spring will actually end up 2.5 meters long, because you add the 1.5 to the 1. That's how you come up with the 2.5. Okay, but the question was, well, how how far will the 45 force stretch the spring? You could say 1.5 meters beyond its natural length. Okay, we got the rope problems. These are typical problems involving a rope, usually, or sometimes I should say the rope has some weight attached to the end of it. Okay, the rope has a weight associated with it per distance. So in this case, kilograms per meter. Okay, but so let's take a look at how a problem like this would be solved. It says a 5 kilogram bucket is lifted from the ground into the air by pulling in 20 meters of rope at a constant speed. The rope weighs 0.08 kilograms per meter. How much work was spent lifting the bucket and rope? So here's a case where we're going to use the work formula. Now for force, our force is going to be mass times acceleration, and our distance is d. Okay, so our mass is 5 kilograms. Acceleration will be the acceleration due to gravity, okay, which is 9.8 meters per second squared. And then there's going to be, so we're going to do two things. We're going to figure out what's the work involved to lift the bucket, and we're going to figure out what's the work involved to pull up the rope. Okay, two things at play. Okay, so first let's tackle the bucket. That's the easier of the two. So we have the 5 kilogram for the bucket. We're going to multiply that times 9.8. So if we multiply that times 9.8, we get 49. 49 newtons. So that's like our force. And then we take that and we multiply it by, it's going to be moving 20 meters, right? We multiply that times 20. That gives us 98, so 980 joules. Okay, so that's for the bucket. Now the work for the rope, that's going to involve an integral. And the typical integral for a rope, because what happens is when you have the 20 meters of rope in the beginning, it's going to be a lot more weight you're pulling. As you pull the rope, and as this bucket starts going up, you have less and less rope that you're pulling. So you have to factor that part into it as well. So there's this typical formula we use with an integral. So we say we have an integral. We set up the integral. It'll be from 0 to 20 because we're pulling in 20 meters of rope. We often factor this into play. This is the weight of the rope, right? It weighs 0.08 kilograms for every meter of rope. So that goes in front. We often put a function here. The function is going to be comprised of the length that you start off with minus x. So we have 20 minus x. And that signifies that at any point in x, any distance you give, you're going to get the remaining rope that you have left to pull up. And then we also factor in the 9.8 for the acceleration dx. Now, one thing I want to mention here, when you're doing SI units, you have to factor in the 9.8. When you're doing American or British units with pounds and feet, you don't have to factor in this 9.8. Okay, because the way we get our weight factors in gravity as well. Right? That's how we know how much we weigh on Earth, right? We take our mass and we multiply by some amount of gravitational pull, right? In our case, 9.8 meters per second. And that gives us our the amount of force, right, that we're exerting on the ground. So with units like American or British units, we don't use the 9.8. I just want to be that clear. Okay. Okay, so now let's do this. Let's distribute the 9.8 and the 0.08 into the parentheses. Okay, you could use a calculator for this part. I know we mentioned no calculator, but for things that involve decimals like this, you can, and especially if you're doing the homework, as you guys will see, go ahead and use the calculator. Don't go nuts over trying to work it out by hand. So I went ahead and did this already, so I have 15.68 minus 0.784x dx. Okay, so when we integrate this, we get 15.68x minus 0.392x squared. Okay, we plug in the 20. When we plug in the 0, we see we get 0. And so if you work this out, you end up with 156.8 joules. Add the 980 that was for the bucket. And we end up with a combined 1,100 36.8 joules. Okay, let's take a look at our next one. This is also part of a family of problems, very popular problems. They usually involve tanks of some shape. This is a conical tank. Conical tank is often used. And the diagram is here to help us process the problem. The conical tank is filled to within 2 feet of the top with olive oil weighing 57 pounds per cubic foot. How much work does it take to pump the oil to the rim of the tank? Okay, so we start off with basically picturing that we have these circular layers of oil, if you will. Okay, each circular layer is going to have a thickness, we call it delta Y, and we have basically we have a volume, like a small volume of each circular disc of these. Right, it's going to have an area of the circle times a thickness, and that'll give us a volume. Now, for our case, it says, now according to the cone has a height of 10 feet, as you guys can see from the diagram. Okay, the tip of the cone goes up to 10. Top of the cone is up to 10. And then we're going to have a series of these circular slabs, and because it's filled to within 2 feet of the top, that means this is currently filled up to 8 feet. Okay, so the way you set up the integral will be from 0 to 8. Okay. Next, we have to come up with the formula. We have a formula for each of these slabs. Right? To get the formula, we take and we try to figure out what the volume is of each of the slabs. Right, so let's put that off to the side here. We call it delta V. So to get delta V, we do pi times the radius squared times the thickness. Right, and the thickness, we call it here delta Y. So according to this diagram, we have pi. Now the radius is, if you look at the circle, they're giving you a radius of half Y. Okay, so half Y squared delta Y. Okay, and the way we get the half Y is they give us this line equation, says Y equals 2x. And then if we manipulate that, we get x equals 1/2 Y. Okay, so now if we go ahead and we expand what this is, we get 1/2 Y times 1/2 Y, which is 1/4 Y squared. So we have pi times 1/4 y squared delta y. So another way to say it is pi over 4 y squared delta y. So next we need to get an expression for the weight. Now our weight, let's say a weight in terms of y. So we're dealing with the y's here. W of y. We have the olive oil weighing 57 pounds per cubic foot. And so we take that weight and we're going to multiply times the volume, the delta V. So we have 57 times, now delta V was pi over 4 y squared delta y. Okay, so if we put this together, this gives us 57 pi over 4 y squared delta y. So to figure out now the next part comes from the distance through which this liquid has to act in order to get to the level of the rim of the cone. Okay, so the way we do that is we look at the height of the cone, 10, and to figure out the distance, we minus the y. Right? Anytime we minus the y, it gives us the distance from the top. Okay, so here's the setup for it. We have the work, the weight, we should say, the weight for the liquid, which is the 57 pi over 4 y squared. And then we have the function for the distance, which is 10 minus y. You could think of this function as the function we used for the rope problem. Remember the rope one, we said it was 20 minus, was it 20 minus x? So it kind of follows that same path. Right, this is the amount, this is how you get how much you need to go to the top of the cone. And then the delta y would be dy. Okay, so that would be the setup to the problem. Okay, it's important to set up the delta v first, and that way you could then insert that along with the distance function, and then you could integrate. Okay, so I'm going to continue that down here. The 57 pi over 4, that's a coefficient, we can move outside. And so the y squared 10 minus y dy. Okay, distribute the y squared into the parentheses. So we have 10y squared minus y cubed dy. And now we can integrate this. So that means we end up with 10 thirds y cubed minus 1/4 y to the 4th. And then we plug in 8 and 0. Okay, so I pre-plugged this in earlier, and I worked it out. I multiplied through with the 3.14 pi, and I end up with approximately 30,561 foot-pounds. Okay, but this is the general setup for it. All right, any questions, just write me an email or bring it up during class. Have a good day, have a good night. We'll see you soon.